Welcome everyone. Today we're going to talk about tree-based models. There are 4 models that we're going to discuss. First, decision trees. I'm sure many of you are already familiar with decision trees from previous courses. Then the idea of bagging or bagged trees. Then we will discuss random forests. So bagging and random forests are ideas for aggregating a number of decision trees to reduce the variance of the predictions. And then we have boosting or boosted trees. So maybe we first discuss decision trees and then have a break. Then maybe discuss these 2 in a break, and then this is the last topic. But there's also some sort of byproduct that we can have from tree-based models. That's a simple plot showing importance of models for the predictions in our tree-based model. So we will discuss this as well at the end of today's lecture. Any questions before I start? No? All right. So let's start with decision trees. We can have decision trees for classification and for regression. Let me first give you an example about the decision tree for classification. So I think when we discussed classification earlier, the example was on predicting whether a fish of certain weight and length is a tuna or a salmon. So let's say that this is the feature space, the space of predictors. We have 2 predictors, x1 and x2. x1 is length of fish. And we have x2 here, which represents weight. And based on our historical data, let's say we have these examples representing tuna. So this means an observation of type tuna. And as you can see, there's positive correlation between weight and length, as it is expected, right? So a fish that is longer tends to be heavier as well. And then let's say we have also these observations belonging to a different class. And this means salmon. Now if we want to use a tree-based model for making predictions based on this scatter plot, one idea is to simply segment the feature space using a couple of vertical and horizontal lines. So maybe the first line that allows us to separate this feature space into 2 regions with more homogeneity in terms of the classes, maybe a line like this, a vertical line like this, could be useful because we can see what is to the left of this line is just tuna. So now we have a region which is totally pure, which is totally homogeneous. So we have this value L1, and in our decision tree, which is like a flow chart for making decisions, we can simply check whether the length of the fish we want to make a prediction for is smaller than L1 or larger than L1. If it is smaller than L1, we end up in this homogeneous region where everything based on our historical data is tuna. So it just makes sense to predict it as tuna. That's it. But if the length is larger than L1, I guess we need to ask more questions. We need to check more information about that test case. So that's why our decision tree could be something like this. The first question we ask for a test case is whether length is smaller than L1. And there are 2 possibilities. So here, this is for yes. I'm just drawing the decision tree such that yes answers are to the left. And this is for no. So if length of a fish is smaller than L1, so this is some, let's say this is some unknown fish that ends up here. And its length is this much, smaller than L1, right? So then here, essentially, we have a terminal node. So in this terminal node, we say, essentially, we end up in region R1. So this is region R1, where we have homogeneity in our class. This is a class where all the historical data are tuna. So it just makes sense to predict the class as tuna. But what if the length is larger than L1? If the length is larger than L1, we will be in this region to the right, and then it kind of depends whether we are, let's say, above this line or below this line. So just to make the example a bit more interesting, I'm going to also consider there's a historical data of a salmon here and a tuna here. So this line is some W1. So we're checking, so in here, we don't have a terminal node. Here we have an internal node because we're splitting the space based on some question about a feature, some question about a variable. So we ask whether the weight of a test case is smaller than W1. If it is smaller than W1, so this is yes, we will be here. So let's call this region R2. And as you can see, it's not, totally pure, it's not totally homogeneous, but just, observations of salmon are, outnumbered, more common, much more common than this one observation of tuna. So let's say that for the sake of, making prediction, this region is homogeneous enough, and we're going to make this, more solid a bit later. So in this region R2, we're going to predict the type as salmon. And if the answer to this question is no, this means that we are in region R3. And for region R3, as you can see, again, the region is not perfectly homogeneous, but most of the observations in this region are tuna. So it just makes sense to predict this as tuna. So this is a decision tree. As you can see, it's very intuitive. It is meant to represent, the process that some people follow for making a decision. So it is highly interpretable, right? So our model is just this flow chart. There's no equation. For the final model, it's just this. So if someone who's not from a, let's say, technical field wants to use this model, it's really easy. We can actually maybe, to some, let's say, fisherman who doesn't know anything about engineering or, let's say, data science, we can just say, all right, you just need to answer these questions, and that would tell you whether the fish is a salmon or tuna. But I guess for a real fisherman, they know much better, much more than us about fish than really, using this. They can just look at it and say whether it's a tuna or a salmon. All right, any questions? No? All right, so in this example, we covered decision tree for classification, but we can also have decision tree for regression. Just to give you an idea, let's say we have our feature space here. We have x1 representing, let's say, the square feet of an apartment, and x2, maybe the number of bedrooms, right? So our feature space would be, let's say, something like this. As the number of bedrooms is kind of discrete, we may have data like this. Because the number of bedrooms is just, one of some set of integer numbers, I guess. So these are our observations. And there's also some quantitative variable or response, y, which is price. So we want to predict price based on these features. So as you can imagine, so this is, let's say, number of bedrooms, and this is the square feet. Here, again, with a couple of horizontal and vertical lines, we can make this, segment this feature space. Let's say first this line, then maybe it makes sense to separate, small apartments. Then maybe we have this line, then maybe this line, and so on. And then for each of these regions, y is relatively, similar. So let's say y, price of this apartment is close to price of this apartment. So the homogeneity of the regions, we cannot see it, but they are relatively homogeneous. Then the idea is that for making a prediction, we're going to see whether we are in, let's say, R1 or R2 or R3 or R4 or R5. We're going to only have 5 possible regression predictions here. For some sample observation, we're going to see where it ends up. If our sample observation, let's say, ends up here, based on x1 and x2, it is in region 5. So as a prediction, we're going to take these observations in region 5 and take mean of yi if I belongs to region 5. So that would be our prediction. So that's how decision trees can be used for regression. It's pretty much the same idea. We need to segment the feature space. And then these regions are essentially regions where the observations are relatively homogeneous. Therefore, for making prediction, we just need to follow a couple of questions to see where our observation ends up. For example, in here, then we just take the average of the y values for training data in that region and just return that as the prediction. Any questions? So this is how decision trees can be used for regression. So for the rest of today's lecture, I'm going to just move between classification and regression every now and then, but pretty much whatever we talk about is valid for both cases. It's just the loss function that is different. So for classification, we work with loss functions like Gini impurity or Gini index, or other loss functions like we have we have cross entropy also for classification. But for regression, we would use simply RSS, the residual sum of squares, to see whether how homogeneous the regions are. All right. So one issue with decision trees is that they are generally prone to overfit. Why do you think this is the case? Yeah. So if you just want to find these homogeneous regions and we let the tree to just grow, we're going to have more and more of these horizontal and vertical lines up to the point that each region is going to only have one observation in it. That would be fitting hard to the data. That would be the case where for example, for separating this one, maybe we draw some vertical line here and then a horizontal line here, right? So that would be a model that is too complex. So one issue is overfitting, and for preventing overfitting, there are a couple of ideas. One idea is to have some minimum number of observations per region. Let's say minimum number of samples per box or per region. This means that if we are in a region like R3 and we see that R3 already has only 8 observations, it doesn't make sense to segment R3 anymore because that would be fitting hard to the data. So this is one kind of general requirement that we're going to have in our tree growing process. So we don't let the tree just grow, infinitely. We stop it wherever we get to a region that has, let's say, 8 or fewer observations in it. And another sort of parameter that we can control is like depth of the tree. So the depth of the tree is essentially a hyperparameter for a decision tree, and we can tune it using cross-validation. So in terms of bias variance trade-off, the error would have some pattern like this, and the depth of the tree is some measure of complexity of the model. So with cross-validation, we can get MSE cross-validation or some other measurement of error, let's say for classification, and see this is the region where we want to be. So this is the suitable value of D star if we want to use a decision tree, so that we don't overfit to the data. Yeah. So minimum number of samples per region would be something like this. In region R3, here we have 8 samples. And this means that because of this stopping criterion, where we get to this, regardless of how homogeneous or heterogeneous this region is, we're not going to split it anymore. Depth of the tree is the number of splits. So here, for this tree, number of splits is 2, or depth of the tree is 2. The way we can think of it is that this is one level, and this is a second level. So depth is this, because in computer science, trees are upside down. So this is the root of the tree. This is, strangely, the leaves of the tree. And from the ground, which is here, to the leaves, that's the height of the tree. But as the trees are upside down, we call them depth of the tree. So here, it's essentially the number of splits. And D plus 1, which is 3, would be the number of leaves. Leaves are the same thing as terminal nodes. So some terminology. So here we have 3 terminal nodes, and we have a depth of 2. Yeah. Yeah. The depth would be, I guess here, in this case, depth happens to be same as number of splits. but it's not always the case. Yeah, you're right. Yeah, yeah. But usually we represent D. We use D to refer to number of splits, not really depth of the tree. So maybe it's just better to forget about depth and just call this number of splits. So D is the number of splits for what we talk about in this course. All right, any other questions? So, all right, so now the process for growing a tree. So the process for growing a tree is simply, a greedy algorithm that tries to, make some improvement to the loss function in every split. So, in the case of regression tree, our loss function would be RSS. So we want to minimize RSS, and RSS is equal to sum of y hat I minus yi squared over n data points. So essentially in each step, all right, so minimizing this, so this is minimizing it over some really unusual space. So let's say it's minimizing it over some space S. S is the space of possible segmentations. It means different ways that we can create boxes for that feature space. And as you can imagine, this is a huge space of possibility for our optimization model. The feasible space is just huge because you can just create these boxes in very different ways. You can use different number of boxes, and also you can decide on their limits differently. That's why the space is just huge, and solving this to global optimality is just very challenging. So that's why we're going to solve it using some heuristic method. So we use a greedy approach called recursive binary splitting. Some top-down greedy approach, which is called recursive binary splitting. So with this algorithm, essentially in each step that we're making a split, we try to minimize the function as much as possible. Only for that step. That's why this is some sort of local optimization. So this was the case of regression for a classification. What sort of error do you think we can use as a loss function? Anyone? So here now we have different classes, and RSS doesn't really exist like this. We have a different type of error. Yeah, that's right, the final answer, but I was hoping to get something like misclassification error rate. So similar to RSS for regression, we have misclassification error in classification, but the issue with misclassification error rate is that it's not sensitive enough. When you make one change to the predicted classes, the misclassification error rate doesn't change as much as we ideally want. Therefore, we need a more sensitive loss function, and one sensitive loss function is Gini impurity, or Gini index. Another loss function is cross entropy. So the process is the same. We use this top-down greedy algorithm, the so-called recursive binary splitting, so that whenever we're considering to make a split, we decide on that such that Gini impurity has the highest reduction, or cross entropy has the highest reduction. So Gini index or Gini impurity is defined like this. So for classification, we're always predicting based on the most common class in a region. So when we are in a region Rj, there's going to be some class K. There's some class K for which just p hat of K is larger than all the other p hats. Just the probability, just the likelihood of that class is larger than all the other classes. So in region J, we predict based on class K. For example, in that example up there, in region 1, class tuna is more likely, and its likelihood is 100%. Now question for you. What is the most likely class in region 2 up there? Class salmon. And in region 3, tuna. So for example, in region 3, p hat of tuna in region 3, let's say in region 3, it's 7/8 because there are 8 observations and 7 of them are tuna. So this is what p hat means. So now Gini impurity is the sum of p hat k times 1 minus p hat k for a region like Rj over the classes k equals to 1. So this is small letter k to capital K, which is number of classes. For example, for that scatter plot, it was binary classification. We only had 2 types of fish. Therefore, capital K was 2. And this is just Gini impurity that measures how homogeneous a region is. I can give you a couple of examples. For example, in region 3, p hat of tuna is 7/8. Therefore, Gini impurity or Gini index would be 7/8 times 1/8 plus 1/8 times 7/8. So it's 14/64. Does it make sense?
And we'll try to minimize this.
Yeah. This is I mean, yeah, this is relatively a small value in here because this value actually has some interpretation. So if you're interested, this is the probability of misclassifying something if we were to classify it based on the distribution in that region. Sorry if this is a bit complicated, but this is just an interpretation for this loss function. So let me just explain it with the example. So this interpretation can sometimes help to understand what's going on, but also there's a risk of the example confusing you. So if it's not intuitive for you, don't worry about it. So in region 3, when we are in region 3, we're going to classify as tuna. That's it. But in this example, I'm talking about some hypothetical situation in which we would classify based on the distribution of tuna and salmon. The distribution is 7 to 8, 7 tuna, 1 salmon. If the distribution is 7 to 8, this defines the probability of misclassifying an observation in that region. Because with a probability of 7/8, we would classify it as salmon, and then there's 1/8 probability of being unlucky and the observation being actually the tuna. So this is one way of misclassifying. The other way is that if we classify the observation as a salmon, but the observation is a tuna. So in these 2 cases, we would make an error. So Gini impurity is essentially some measurement of our misclassification rate if we were to classify based on the distribution, something that we actually don't do. So this Gini impurity becomes 0 here. So in region 1, which is totally homogeneous, Gini impurity becomes 0, which is perfect because we want to minimize it. Here, Gini impurity would be 0 times something plus something times 0. Does it make sense? All right. So in that example, Gini impurity is not 0 simply because region R3 is not totally homogeneous. But you can see that it's relatively homogeneous. You might be wondering how homogeneous it is. It's this much homogeneous in a sense. Yeah?
I think I understand why the misclassification error is not sensitive.
Yeah. So the misclassification error, when we have a region, with let's say a large number of observations, which is which should be the case for supervised learning, something like this. The idea is whether to split this or not. The thing is, if they are distributed like this, misclassification error, let's say here, it's 50%. And if we also split here, it would be 50% again. You can see that it doesn't change that much, even if these subregions are more homogeneous. But Gini impurity and cross entropy, they are just more sensitive because they are the product of P. So Gini impurity is product of P hat times 1 minus P hat. So when P hat decreases, this thing, when P hat increases, which is what we want, this thing increases in some sort of nonlinear way. When P hat increases, this thing decreases in a nonlinear way. That's what I meant to say. That would make it a suitable loss function, more suitable than misclassification error rate. All right, so all of this was just about Gini impurity. So another loss function is cross entropy. So for cross entropy, it's something like this. It's negative sum of p hat k. So this is for some region. Gini impurity is like for some region Rj. Also here, for each region, we have some value for it. It's minus sum of p hat of k times log of p hat of k from 1 to capital K. So this turns out to behave very similarly. This tends to behave very similarly to Gini impurity, because we care about this loss function decreasing when probabilities increase. So when the region becomes more homogeneous, well, it's not probabilities increasing because they add up to 1, so they cannot all increase. When they become more different, right? So the worst situation for a region is, let's say in binary classification, the worst situation is if we have half and half. If we are in a region where half of the observations are tuna and the other half are salmon, then in that case, Gini impurity is going to be half times half plus half times half, which is half, right? So this is a region which is just worse for the sake of prediction. And cross entropy in such a situation would be minus half times log of half, right, times 2. So it's this. So this is going to be also, so this is negative, right? So the total will be also some positive number. Any questions? Yeah.
So you mentioned that like the 7/8.
Yeah.
Is the probability we classify this as the
7/8 is, this is the situation where we are predicting based on the distribution. So when we want to make a prediction, we're going to just roll a 8-sided die and see what we get, right? 7 out of 8 times we get, numbers 1 to 7, and then we would classify as salmon. 1/8 time, sorry, we classify as tuna. 1/8 time we get 8, and we classify as salmon. And then this thing takes care of situation when we would be incorrect.
But in practice, we just compare, we just select the class with highest.
Exactly. So this hypothetical situation for Gini impurity has nothing to do with how we use a decision tree in practice. In practice, it just makes sense to go with the most likely class. But the explanation of Gini impurity talks about some hypothetical situation where we classify based on distribution. Yeah. Good question. So the thing is, I guess for classes that are not in that region, p hat of k is 0. So it's same thing. So the sum is general, it's for all the classes, but both for Gini impurity and for cross entropy, this thing becomes 0 for classes that are not represented at all in a region. Any other questions? All right. Yeah. So I have one more topic to discuss about decision trees, and then we can have a break. So we discussed how to grow a tree, but if you grow a tree like that, it's going to just overfit to the data because it just wants to minimize RSS or minimize Gini impurity or minimize cross entropy. So it just does a lot of splits to just get really homogeneous regions, and for which we have 0 loss function. That would be a tree that is overfit to the data. And another idea for for getting a suitable sort of bias variance trade-off, sort of a suitable trade-off between underfit and overfit, is first growing the tree, maybe with some really kind of relaxed restriction that that we don't split when the region is just too small. When the region has, let's say, less than 8 observations, we stop, right? But other than that, we let the tree grow as deep as needed. We let the tree have as many splits as it wants, and then we prune the tree. So we let the tree grow deep, and then we start, just cutting leaves from the tree. So for pruning the tree, we have another process, right? So first, the statistical software is going to take care of all of this for us. So we don't really, do these steps. But just to get a sense of, how decision trees are fit so that they don't overfit despite, their kind of tendency. The algorithm that, fits a decision tree to a data set first, does recursive binary splitting and gets some bushy, large tree, deep tree, and then prunes it so that we have some suitable trade-off of complexity and fitness. So for pruning the tree, in the case of regression, we can have some loss function like this. That we want to minimize, so this part is like RSS. And we add some lambda times t. This lambda is, the pruning hyperparameter. And t is the number of leaves, or number of terminal nodes. So this is the same thing as d plus 1. If d is the number of splits, if d is the number of splits, then this absolute of t is number of leaves or number of terminal nodes. So in your textbook, this parameter is represented as some alpha, but it's just some hyperparameter. So this alpha in here kind of defines our preference for having a sort of a bushy deep tree versus fitness. Because in order to minimize this whole objective function, this one is minimized when we fit hard to the data, and this one is minimized when we fit very loosely to the data. Actually, if there was no first term, this thing is minimized where t is as small as possible, which would be just one split. So the simplest tree that we can have is this. This is the simplest tree. It's a tree where I guess d is 1 and number of terminal nodes is 2. There's another name for it. It's a stump. So with this algorithm, with an algorithm that minimizes this, we're going to then prune the tree. So this essentially gives us some plot like this, right, where we can see that MSE, the mean squared error in the case of regression, is minimized somewhere for a certain number of terminal nodes. And this is where we want to be because this part is overfit and this is underfit. So we want to be in here where we have some optimum value of T star. But in reality, when we have access to more advanced tree-based models, we're not going to really spend that much time improving a decision tree, because a decision tree eventually has some limitations in the predictive accuracy. So this is pretty much a summary of what we can get out of a decision tree, but later when we learn about random forest boosting and bagging, I guess it would be really, in most practical situations, we would just use a boosted tree or random forest and wouldn't really worry too much about fitting a decision tree just right. Yeah?
Previously you mentioned there are two methods to use overfitting, like minimize the sample. Like we set certain sampling rate and the number of. So that's a more general, and this one is specific to the decision tree.
Yeah. So for this, so whatever we discussed, it was just decision tree. For preventing overfitting, there are different strategies. This is some sort of really minimum requirement. This is sort of a very relaxed requirement. We try to always have this, so that the tree doesn't end up creating regions with one observation. This is really important. We always include it in whatever strategy we're implementing. Then I think that the two alternatives are either tuning the number of splits directly using cross-validation, and then just growing the tree based on the suitable value of d. And then another idea is first growing the tree as relaxed as possible, and then pruning it back based on this idea, which is called cost complexity pruning. So this thing is called cost complexity pruning, because the objective function is some sort of cost function that kind of includes some idea of complexity. We don't want the tree to be too complicated. So this is an alternative. But both of these are just about decision trees. That's why eventually we will focus in practical settings. We focus our attention to advanced tree-based models like random forests and boosted trees. Any other questions? All right, let's take maybe a 5 to 10 minute break, and then we continue.